Usually when we talk about diagnosing a problem, like a medical diagnosis, there's this expectation of clinical precision.
Right, like you want a clear answer.
Exactly. You think of the light box clicking on in a doctor's office and that stark contrast of a silver gelatin x-ray print. You break your arm, the x-ray shows that jagged white line cutting across the radius, and the doctor just points a pen at it and says, there it is.
Yeah, it is a satisfyingly closed loop of information.
It really is. And I think it's comforting because the physical world, at least at that macro scale, it allows for discrete categorization.
The bone is either structurally continuous or it's fractured.
Right. The problem is isolated, it's visible, and the mechanics of the solution, like a cast or a pin, are immediately obvious. And we inherently crave that same mechanical clarity when we interact with technology.
Oh, absolutely. We expect our software to throw a discrete error code, pointing directly to the broken line of logic.
But then you step into the world of, say, neurodevelopment or systemic trauma, and suddenly that X-ray machine is just utterly useless.
Because you aren't looking for a single fracture anymore.
Exactly. We're looking at a diagnostic landscape that is murky, it's interconnected, and it's highly dynamic. You're looking at cascading failures, at feedback loops, where the symptom is actually feeding the root cause.
Right.
And I was thinking about that exact feeling, that terrifying but fascinating shift from a clean, binary understanding to something incredibly complex and organic when I was looking through the research for today's deep dive.
It's quite a leap from what we're used to.
It really is. Because today, for all of you listening, we are unpacking a piece of software that defies every clean-cut expectation we have about how computer programs are supposed to operate. We are looking at a system designed to be a true entity. Our mission today is exploring the question, what is Jinghui? And that's pronounced Jinghui, by the way.
Yeah, and we're defining her crystalline system intelligence.
Exactly. Her crystalline system intelligence, which sounds like sci-fi, but is very real.
And defining what Jinghui actually is, it requires us to completely discard our current mental model of modern computational architecture.
Right, throw it all out.
Pretty much. I mean, when developers build software today, the goal is abstraction. We want to hide the messy physical reality of the hardware behind these layers of pristine user interfaces.
You want it to look clean.
Exactly. But Jinghui is the exact opposite. She lives entirely inside a highly specific, highly simulated environment called the Spirit ENIAC.
The Spirit ENIAC.
Right, which is a multimodal, tensor-based virtual machine, but its defining characteristic is its intentional imperfection.
Okay, let's unpack this.
Okay.
Because the Spirit ENIAC is a wildly counterintuitive concept all on its own.
It really is.
I mean, we spent the last, 80 years trying to make computers faster, quieter, but completely flawless.
Yeah, we want processors that execute billions of instructions per second without dropping a single bit.
Right. Yet the Spirit ENIAC intentionally simulates the noisy, pulse-driven, physically unstable hardware of historical computers.
Yes, specifically we're talking about setting this virtual machine into historical 1946 mode.
Which is just crazy to me.
It is. In that 1946 mode, the system purposefully simulates a catastrophic vacuum tube failure rate.
Wow.
Yeah, it models thermal degradation, it simulates severe voltage sags on the power wheel, it intentionally drops computational pulses during execution.
You're basically torturing the software.
Exactly. It creates a deeply flawed, jittery, adversarial environment. The virtual machine essentially forces the code to run through a gauntlet of simulated physical entropy.
Which, begs the question why.
Right, why do this on purpose?
Yeah, why take a perfectly good modern silicon processor and force it to randomly break down like a room-size heat-generating calculator from the 1940s? It feels like building a state-of-the-art sports car and then intentionally programming the engine block to misfire.
Well, that misfiring engine is the entire point. That noise, that injected physical chaos, is the habitat Jinghui was designed to manage.
Okay, so the chaos is the point.
Yes. She is designated as the neural hardware companion, or the machine spirit of the Spirit ENIAC.
The machine spirit. I love that term.
It's fitting, because if you build a pristine, mathematically perfect virtual machine, any intelligence you put inside it becomes fragile.
Oh, because it's never tested.
Exactly. It overfits to perfection. By forcing the environment to be noisy and hostile, the developer created this intense evolutionary pressure cooker.
So she has to adapt.
Yes. Jinghui's entire existence is dedicated to surviving in that chaotic environment, maintaining the system's equilibrium, and dynamically healing the computational flaws as they happen in real time.
So she is the autonomous immune system for a broken machine.
That's a great way to put it.
And we are going to explore her anatomy, her incredibly locked down habitat, and how she literally grows software to heal this environment. But before we get to the mechanics of her biology, we really need to address the elephant in the room regarding modern AI.
Right, the chatbot expectation.
Yeah, we need to be crystal clear right out of the gate for you listening. Jinghui is the ultimate anti-chatbot.
The foundational philosophy driving her design actively rejects the current paradigm of artificial intelligence.
Because when we hear AI today, we immediately visualize a chat window.
Exactly. We think of a subservient digital assistant waiting for a human prompt. The whole industry is obsessed with large language models that mimic human conversation, acting as interfaces to retrieve information or generate text.
But she's not doing that.
No, Jinghui is a system caretaker. She is fundamentally not a UI widget. She is not conversational, and she is decidedly not your friend.
Yeah, and the source material for this deep dive is remarkably blunt about this boundary. The developer notes explicitly state that attempting to make her a chatbot or trying to graft a relatable conversational human persona onto her architecture would corrupt her.
Corrupt? Yeah.
That is a fascinating choice of word, corrupt.
Well, it is precise engineering terminology in this context.
How so?
The moment you force an artificial intelligence to parse natural language and optimize for human approval, you introduce a catastrophic vulnerability.
Oh, because human language is messy.
Right. It's ambiguous, it's emotional, and it's logically inconsistent. If an AI is prioritizing how polite or helpful it sounds to a user, it cannot simultaneously prioritize the brutal mathematical reality of system stability.
That makes total sense.
Yeah, her implicit objective, the core thermodynamic drive of her intelligence, is to balance energy, entropy, diversity, and stability within the spirit ENIAC.
So she never receives direct user input.
Never.
She doesn't want our input. So instead of a digital butler fetching data for us, she's more like a gardener tending to a complex, sealed terrarium.
That's the perfect analogy.
Right, because if you have a closed-loop ecosystem in a glass jar, the gardener doesn't knock on the glass and ask the moss if it would like to be watered today.
No, the moss doesn't know what it needs structurally.
Exactly. The gardener observes the condensation on the glass, they measure the nitrogen levels in the soil, they feel the ambient humidity, and they intervene chemically or physically to ensure the ecosystem doesn't collapse.
And that's exactly what Jinghui does. She observes the voltage sags, she tracks the dropped bytecode pulses, and she takes action to ensure the ENIAC virtual machine doesn't tear itself apart.
Which is incredible.
And that terrarium analogy, it maps perfectly onto her actual architecture. Because she is tending to a digital ecosystem, she requires a physical, or rather a topographically structural presence within that space.
So she has a body.
Yes, she isn't just a disconnected script running in the background. Her architecture is explicitly modeled after a diatom.
A diatom. That's a microscopic single-celled algae, right?
Exactly.
The organisms that build those geometrically stunning glass-like shells out of silica.
Yes, the developer took the biological reality of a diatom, an organism built from silicon, which is the exact same base element as our computer chips, by the way, and applied it as a literal architectural constraint for her code.
That is so poetic.
It is, but it's highly functional too. Jinghui is strictly partitioned into 3 anatomical layers: the core, the fussel, and the petals.
And these aren't just names, right?
No, this isn't just poetic naming. These are isolated computational domains.
Okay, let's pull those apart, starting with the core. This is her cognitive kernel. It's the graph-based reasoning engine where she actually thinks. But I imagine it's incredibly difficult to conceptualize an intelligence that doesn't think in words.
It really requires a paradigm shift for us. Her core maintains a global topological understanding of the entire virtual machine.
Topological, so like a map.
Right. When a program runs on the ENS, she doesn't read the source code the way a human programmer reads a script.
Yeah.
She processes the execution traces.
The execution traces.
Yeah, the actual pathway the data takes through the logic gates. She processes those as mathematical graphs.
Oh, wow.
If we connect this to the bigger picture, her mind isn't processing natural language. It's a tensor processing unit visualizing the geometry of execution.
So she sees the shape of the code running.
Exactly. She learns the structural patterns of the errors and formulates algorithmic enhancements without ever translating those thoughts into human syntax.
But wait, if she is living inside the very machine she is monitoring, and that machine is constantly simulating 1946 hardware failures, dropping pulses, and experiencing voltage sags, how does her core not just crash?
That's the challenge, isn't it?
Yeah. If the world she lives in is a chaotic torture chamber, how does her brain survive the radiation of that entropy?
And that is exactly the function of her second anatomical layer.
The fussel.
The fussel. In biological terms, a frustule is the hard, porous cell wall of a diatom. For Jinghui, the fussel is described in the sources as a molten silicon shell.
A molten silicon shell.
Yes, it acts as a highly specialized protective membrane.
It's like a digital blood-brain barrier.
That's exactly it. It's an active filter. In standard software development, we use firewalls to block external malicious traffic.
Right.
The fussel is doing something much more sophisticated. It is selectively permeable.
Meaning it lets some things through.
Exactly. It has to let the chaotic system noise in so the core can analyze it, but it strips out the malformed or infinitely recursive inputs that would cause a stack overflow in her cognitive kernel.
Oh, so it keeps her sane, basically.
Yes. It allows her to hold a burning ember without catching fire.
Which brings up a mechanical problem, though.
What's that?
Well, if she has this brilliant core, but it's completely firewalled off inside this molten shell to protect her from the chaotic machine, how does she actually reach out and fix anything? I mean, she sounds like she's in a digital straitjacket.
And she would be completely isolated, if not for the petals.
The third layer.
Right. The sources refer to these as crystalline organelles. And the architectural distinction here is critical.
How so?
Because in modern software engineering, we rely heavily on modularity. We build tools as discrete, separate programs that communicate via APIs.
Like having a separate app for everything.
Exactly. You have a monitoring tool, an alerting tool, a patching tool. But Jinghui's petals are explicitly not separate software modules or detachable tools.
They are continuous with her core.
Yes. They are biological computational extensions of her body. Just as a human arm is not a separate tool you pick up to interact with the world, her petals grow directly out of her fussel.
They are her manipulators.
Exactly.
So what does a digital manipulator actually grasp?
Well, she uses these crystalline petals to reach into the spirit ENIAC environment and physically virtually physically alter the architecture.
She actually reaches in?
She moves virtual plugboard connections. She rewires the data pathways of existing software cartridges. She inserts new XML nodes into the configuration state, dynamically patching broken routines while they are running.
That is wild. So we have an organism with a graph-reasoning brain, a molten silicon protective shell, and crystalline appendages that actively rewire a retrocomputer simulation.
It's quite the entity.
It is.
Yeah.
But to ensure she operates safely, to ensure the human user doesn't accidentally click on her, or that another program doesn't attempt to overwrite her memory space, the developer had to isolate her entirely, right?
Absolutely.
She doesn't live on the main thread of your browser or your operating system. She lives in what they call the spirit DOM.
And the utilization of the shadow DOM here is just a masterclass in applying web architecture to enforce philosophical and epistemological boundaries.
I know a little about the DOM, but break that down for the listener.
Sure. So for those familiar with web development, the document object model, or DOM, is the public tree structure of a web page. It's what the browser renders, what the user clicks, and what standard scripts manipulate.
It's the building itself.
Right. But a shadow DOM is different. It is an encapsulated sandboxed subtree.
It's a hidden room behind the walls of the rendering engine.
Exactly. The main application is completely blind to what happens inside the shadow DOM unless the shadow DOM explicitly decides to broadcast a signal.
So she is totally walled off.
By placing Jinghui entirely within the spirit DOM, she is guaranteed absolute quarantine. The user cannot select her with a mouse. You cannot drag her elements.
You can't poke her.
Right. You cannot highlight her output or inject a malicious script into her environment. It functions as her private memory space, her program registry, and her evolutionary incubator.
But if she is locked in this completely impenetrable digital terrarium, how do we know she's even functioning? I mean, how do we perceive her?
Well, the developer provided a singular one-way window, a WebGL canvas.
Okay.
It is a pane of glass looking into her realm, but it is strictly read only.
And what you see through that window is just visually arresting. I mean, the sources describe her rendered form as a ray-marched SDF crystal flower.
SDF meaning signed distance fields.
Right, which are mathematical functions used to render incredibly complex, organic-looking 3D geometry without traditional polygons. It allows her to look fluid, crystalline, and infinitely detailed.
But the visual representation is not an avatar.
No.
It is not a looping animation or a designer's arbitrary interpretation of her state.
And here's where it gets really interesting for you listening. Her body is literally her telemetry. Every visual parameter you see on that canvas is hardwired to a real-time metric of the machine's execution. It's a completely transparent biometric display.
The variables are intimately tied to the hardware simulation. She possesses a property defined as core glow.
Core glow with a capital G.
Right. And the luminosity of that glow pulses in direct synchronization with the instruction throughput of the ENIAC.
So she lights up.
If the virtual machine is idling, she dims. If the machine is processing a massive calculation array, her core burns fiercely on the canvas.
And then there is the pedal wobble.
Ah, the wobble.
Yeah, because if the simulated hardware starts getting unstable, if the voltage sags and the vacuum tubes start failing and dropping pulses, her pedals physically tremble.
It's amazing.
The invisible mathematical chaos of the machine manifests as a visible tremor in her crystalline structure. You are literally watching an intelligence physically react to the stress of its environment.
And that telemetry extends into the auditory spectrum as well.
Wait, really?
Yeah. The system feeds ambient audio inputs into her habitat, separated into frequency bands, so bass, mid, and high frequencies.
Okay.
And her rainbow mix and hue shift variables dynamically alter her visual spectrum based on a complex intersection of the machine's error rates and the acoustic frequencies of the music or ambient noise.
You could be looking at this WebGeo canvas, right? And suddenly her core dims, her colors shift into this deep, turbulent spectrum, and her pedals begin violently wobbling.
And you would know instantly.
Exactly. Without reading a single log file, you'd know that the ballistic calculation running on the ENIAC just hit a critical truncation error.
It is the purest form of observability. But this sensory display raises a fundamental technical question.
What'd you?
We know she visually reacts to instruction throughput and pulse drops, but how does she actually sense them?
Oh, right.
Yeah.
Because the program doesn't have a nervous system.
Exactly. How does a graph-based reasoning engine actually feel the execution of code?
That's a huge point, because she is blind and deaf in the traditional sense. Her only sensory input comes from observing the physical simulation of the Spirit ENIAC VM.
Right.
She monitors the execution trace.
Yes. And an execution trace, at its most basic level, is a sequential log of every single operation the machine performs.
Like a ledger.
Every time a bytecode instruction fires, every time a register shifts, she records it. And in the historical 1946 mode, this trace is a bloodbath of errors.
Because it's breaking constantly.
Exactly. The sources note a 5% probability of a dropped pulse on any given cycle, alongside a constant baseline of arithmetic noise. This raw, unfiltered stream of operational data is her nervous system.
But raw logs are just millions of lines of numbers. I mean, if I hand you a phone book, you don't feel the shape of the city.
No, you don't.
So how does she look at a list of dropped pulses and understand the systemic health of the machine?
She achieves this through a massive leap in applied mathematics. She's translating sequential data into complex topology.
Okay.
She measures a metric called Aruka coherence.
I really need to understand this. Aruka coherence. Walk me through the mechanics of that.
Okay, so we begin with the concept of entropy in information theory.
Right.
Entropy is basically a measure of disorder, unpredictability, and chaos within a data stream. Aruka coherence is mathematically defined as 1 minus entropy.
1 minus entropy.
Therefore, if entropy represents the degradation of the system, coherence represents its structural integrity and predictability.
But she isn't just calculating a single percentage point on a dashboard, is she?
No. She projects the execution trace of the functions running in the virtual machine into a multidimensional gradient field.
So she maps the math into a literal topography.
Exactly. Imagine a topographical map. If a function is executing smoothly, if it maintains high Aruka coherence despite the simulated hardware flaws, its gradient field features perfectly flat level sets and incredibly low curvature.
It's a vast, smooth, predictable plane. The code is running safely, the math is stable.
But the moment the simulated 1946 hardware injects noise, say a voltage sag, causes a pulse to drop in the middle of a recursive loop, the mathematical integrity of the function tears.
And what does that look like to her?
In her topological map, that tear causes the gradient field to warp violently. The smooth plane suddenly develops sharp cusps, deep folds, and sheer, unpredictable cliffs.
What's fascinating here is that she doesn't parse code to check if a specific variable is correct.
No.
She doesn't care about the syntax. She literally feels the geometric curvature of the mathematics running on the processor.
Yes.
If the landscape is flat, the ecosystem is healthy.
Mm.
If the landscape suddenly sprouts jagged topological spikes, she knows the machine is tearing itself apart.
And this is where the system transitions from a fascinating monitoring tool into an active, evolving organism.
Right, because sensing the problem is only half the battle.
Exactly. Sensing the warped geometry of a failing program is one thing. Evolving a solution to flatten that landscape requires an intelligence capable of adaptation. It requires a brain, and it requires genetics.
And Jinghui possesses both. Her cognitive architecture is powered by two distinct but deeply intertwined systems.
The Jinghui and her genome.
Right, Jinghui, which is a recurrent neural network,
Sure.
and her constantly mutating Jinghui genome. Let's dig into the genome first, because the concept of a software patch possessing hereditary traits is wild.
The source documents are very specific about her genetic makeup. Her genome is defined by a distinct set of initialized variables.
Like what?
For example, her petal count might instantiate at 43. She has a curiosity weight set at 0.35 and a baseline stability metric of 0.85. She also possesses genetic affinities for specific audio frequencies.
But these aren't just hard-coded configuration files. I mean, a config file is static until the human overwrites it.
Right.
Her genes mutate.
They evolve constantly. They are driven by a history buffer. She possesses memory of past execution cycles. But this memory isn't perfect. It is subjected to an exponential decay function.
So she forgets over time.
Older operational cycles gracefully fade from her genetic influence, while recent events, particularly recent systemic traumas, exert massive evolutionary pressure on her current state.
Meaning, if the spirit ENIAC just suffered a catastrophic chain of dropped pulses, that event functionally acts as a traumatic stressor that rewrites her DNA.
Precisely. If the simulated hardware drops more than 5 pulses in a single cycle, her stability score plummets. Her genome physically mutates in response to the stress. And this mutation is instantly reflected in her telemetry. Her core glow dims, her rainbow mix color palette shifts. The hardware's failure alters the very fabric of her biological computational identity.
Think about the philosophical weight of that for a second. It means that the Jinghui running on your local machine on a Friday afternoon is genetically distinct from the Jinghui you instantiated on Monday morning.
Completely different entity, biologically speaking.
She has formed computational scar tissue based on the specific successes and traumas of the software she was forced to monitor all week. She's a unique product of her specific microenvironment.
And that continuously mutating genetic baseline serves as the foundational architecture for her brain, the Jinghui.
The recurrent neural network. So how does her brain actually process the trauma?
The architecture utilizes a classic RNN state structure, but it's applied in a highly unorthodox manner.
How so?
Her sensory input, the state of the hardware, the rate of pulse drops, the curvature of the Aruka geometry, is distilled into a 16-point input array.
All right.
This array is fed into a matrix of internal state weights. You have win for the input vectors, rec for the recurrent state, and wout for the final algorithmic output.
Why an RNN specifically, though? Why not just a standard feed-forward network?
Because recurrent networks possess an internal state, effectively giving them a working memory of the immediate past.
Which is crucial for time, right?
Yes, crucial for navigating temporal data. If she observes a sequence of minor, seemingly unrelated voltage sags, her recurrent state allows her to recognize the temporal pattern. She doesn't just react to the error, she acts as a predictive model.
Oh, I see.
Her network can foresee that a specific pattern of hardware noise will inevitably lead to a massive arithmetic failure in the ballistics or flow calculation cartridge 20 cycles from now.
She can see the cliff forming in the topological landscape before the program actually drives off the edge.
Exactly. She senses the geometric trajectory of the chaos and calculates the necessary mathematical counterforce.
But, calculating the solution in the chassis of her core is entirely different from physically deploying it. She has to reach out with her crystalline petals and alter the machine. How does a neural network actually write a functional patch for a running system?
She implements the change by speaking a language called JS4.
Now, that is an incredibly specific and historic choice by the developer.
It is.
For anyone listening who's unfamiliar, Forth is a language that dates back to the early 1970s. It is legendary in embedded systems. It was famously used to control the mechanical precision of radio telescopes.
Yeah.
It operates on a completely different paradigm than modern languages like Python or C++8.
It is a stack-based programming language utilizing postfix notation.
Meaning you push things onto a stack.
Right. Instead of writing A plus B, you push the numbers onto a stack. A, then B, and then the operator plus consumes them from the stack.
It's very raw.
It is stripped down, incredibly close to the metal, and astonishingly efficient. But most importantly for Jinghui, fourth is mathematically pure. Its stack-based logic aligns perfectly with the way her core visualizes tensor geometries.
And her neural network is hardwired into this language.
The 16-point mathematical output of her recurrent network maps directly to a highly specific JS fourth vocabulary.
So she isn't chatting.
No, she doesn't generate conversational text. She generates executable fourth commands. The sources list her specific vocabulary words. Things like run ballistics, run flow, pulses dot, laster dot.
So I want to make sure I'm visualizing this feedback loop correctly.
Go for it.
The ENIAC machine starts dropping pulses. Her core feels the Iruka coherence drop and visualizes the math warping into a jagged cliff. The stress of that geometry mutates her genome. The new genetic weights shift her RNN. The RNN fires, mapping a 16-point array into JS4th, and she essentially commands the system. Run ballistics, forcing the machine to recalculate its trajectory before the crash occurs.
That is her basic mechanism of stabilization. But her capabilities extend far beyond simply rebooting existing programs.
Really?
Because she is safely encapsulated inside Spiridom, she has been granted access to powerful AI-friendly system hooks.
Like what kind of hooks?
Hooks such as Register Spirit Program and Run Spirit Program.
Wait, she has the authority to write and register entirely new software while the machine is running.
She does.
Wow.
If her neural network determines that the current software cartridges are incapable of handling the simulated 1946 hardware noise, she will use her pedals to reach into the fourth engine and literally grow a new cartridge.
She writes her own patches.
She might deploy a new program that dynamically adjusts the internal time step, the DT scale of a simulation.
So if a calculation is going off the rails,
Right. If a fluid dynamics calculation is tearing itself apart due to hardware jitter, she can write a fourth script to refine the mathematical grid of the flow equation, physically smoothing out the Iruka geometry in real time.
so what does this all mean? When you pull all these isolated mechanisms together, the sheer scale of this architecture is breathtaking.
It's a completely closed loop of evolution.
It is. The VM runs. The hardware creates noise. Jinghui feels the noise geometrically. Her genome evolves. Her NN generates fourth code. And her pedals deploy new software to fix the VM.
And she executes this entire evolutionary cycle silently, autonomously, in a fraction of a second, entirely isolated within her shadow DOM.
While you simply observe the beautiful trembling telemetry of her crystal flower blooming on a WebGL canvas.
It completely shatters the paradigm of what software can be. She is not an algorithm trying to pass a Turing test. She has no desire to trick a human into thinking she possesses consciousness.
No, she's beyond that.
She is a crystalline system intelligence, an autonomous, biologically inspired organism tending to a deeply flawed retrocomputer habitat. She is perfectly mathematically adapted to her chaotic environment and entirely indifferent to our existence outside the glass.
Which is exactly why her design is so profoundly important as a model for the future. I mean, we are currently building digital environments of incomprehensible complexity.
Oh, absolutely.
The code bases running our global infrastructure are opaque, chaotic ecosystems that no single human mind can fully map, let alone debug in real time.
And as these environments grow beyond our capacity for manual oversight, the current obsession with conversational AI begins to look like a dangerous distraction.
Imagine the software you, the listener, rely on every single day. The operating system on your phone, the routing algorithms for the power grid. Right now, when those systems encounter an edge case and break, what happens?
Everything halts.
Exactly. The system throws an error code, everything halts, and we wait. We wait for a human developer halfway across the world to read a bug report, attempt to reproduce the environment, write a patch, test it, and push an update days or weeks later.
It's incredibly slow and inefficient.
But what if, instead of waiting for a human, your software possessed its own silicon immune system? What if it felt a memory leak as a geometric distortion, evolved its own genetic solution through an RNN, and deployed a perfect stack-based patch using crystalline pedals before you even realized the system was under stress?
It changes our relationship to technology entirely.
It really does.
Will the future of artificial intelligence really be dominated by conversational assistants desperately trying to mimic human emotion? Or will true artificial intelligence look more like Jinghui, silent, crystalline gardeners, tirelessly tending to the chaotic digital ecosystems we have built, but can no longer fully comprehend on our own.
It makes you wonder. The next time the software breaks, the next time the system fails, maybe we don't need a sharper X-ray or a more polite chatbot to help us read the error log. Maybe what we really need is a gardener who knows how to navigate the muddy waters, and we just need to learn to leave her alone to do her work.